Assalamualaikum everyone. Today we have to start this section 8-7, which is about piping networks and the pump selections. So in this section we will see that if we connect different pipelines of different diameter in the series connection or in the parallel connection, then what equations we can use for the volumetric flow rate and what should be the head loss in different pipelines. So let us see this figure here, which is about the connection of the pipelines in the series way. So one bigger pipeline is connected with the smaller pipeline. In the bigger pipeline, we can have a friction factor A. The length of the pipeline can be LA, and the diameter of this pipeline can be DA. And for the smaller pipeline, we can have the friction factor B for this pipeline. The length for this pipeline it is LB, and the diameter it can be seen as DB. Okay, now what we assume from this kind of arrangement, then when the fluid is moving between two pipelines, then the volumetric flow rate at the point 1 it can be equal to the volumetric flow rate at point 2. Okay, so we can have the equation from the mass balance that volumetric flow rate at the inlet can be equal to the volumetric flow rate at the outlet. And also in terms of the head loss, it is additive. So the total head loss in these two pipelines, it can be an addition of head loss in the first pipeline plus the head loss in the second pipeline. So for the series pipeline, the flow rate is same in each pipeline, and the total head loss is the sum of head losses in the individual pipeline. So we can see the explanation of these two equations from here. Now let us see another situation in which there is a split of one bigger pipeline into the two pipelines, and they can rejoin at the point B. Now what can happen in this kind of situation? For example, for this pipeline, the friction factor is F1, the length is L1, and D1 is diameter. And the branch 2, we can have the friction factor F2, the length can be L2, and the D is the diameter for this pipeline. Now you can see that this one is the curved pipeline, and this pipeline is having some branch, and it is somehow like changing the shape. Okay, so what we can see from here, that the head loss in the first branch it can be equal to the head loss into the second branch. So what does it mean from the head loss? That the pressure drop that we get here in the first branch, it will be the same pressure drop that we get in this branch. So for this parallel connection, the head loss in one piping system it can be equal to the head loss in the other pipeline or the other branch of the pipeline. And what about the volumetric flow rate? So the volumetric flow rate it will be divided as we can see from the mass balance, or you have taken the courses for the energy in the mass balance. So the volumetric flow rate in the first branch plus the volumetric flow rate in the second branch, it can be a volumetric flow rate at point B and also at the point A. So for the pipelines in parallel, the head loss is the same in each pipe, and the total flow rate is the sum of flow rates in the individual pipeline. There is one more argument that why the head loss in the first branch it should be equal to the head loss in the other branch. As you look at the motion of the fluid which is moving in these pipelines, so the direction of the movement of the fluid is in the right hand side, right? So if the head loss or the pressure drop in one of the branch becomes higher, what would happen? There will be a circulation motion of the fluid within the branches of the pipeline, and the fluid it will not move forward, right? So to make the fluid moving forward, the head loss and the pressure drop in both of these pipelines should be same. However, the volumetric flow rate in both of them it can be different. Now let us solve this equation in slightly more easy manner. So the relative flow rate in parallel pipes are established from the requirement that the head loss in each pipe be the same. Okay, so here we are talking about the parallel pipelines in which the head loss in one segment can be equal to the head loss in the other segment. So for the head loss in the first segment, we have the equation for the head loss, the major head loss, and for the second segment, we can have an equation for the head loss in the second segment. Now we can just simplify this equation and rearrange this equation in the form of velocity. So V1 divided by V2, and then you can on the right hand side you have the rearrangement of the equation. We can also write this equation in terms of the volumetric flow rate. So we multiply this one with the cross sectional area, the left hand side and also on the right hand side, so we can get the equation in terms of the volumetric flow rate, and on the right hand side we can have this equation. Now what we can see from this equation, the flow rate in one of the parallel branches is proportional to its diameter to the power 5 by 2 and is inversely proportional to the square root of its length and the friction factor. So for example, if we take this one, the first line here, what we see is the volumetric flow rate in one of the branch. So the volumetric flow rate in the first branch is proportional to diameter having the power 5 by 2. So diameter power 2 plus multiply by diameter with the power 1 by 2. So overall power you will be getting 5 by 2 for the diameter. So volumetric flow rate will be proportional to diameter having the power 5 by 2 and is inversely proportional to the square root of its length. So this one is L1 is the length related to the branch 1. So it is equal inversely proportional to the length having the power 1 by 2 and the friction factor with the power 1 by 2. Okay, so this is like simple explanation of the dependence of the volumetric flow rate on the diameter, friction factor and the length of the pipeline, and what are the analysis that we can do on the attachment of the pipelines in the parallel manner or in the series manner. First thing, that the law of conservation of mass should be conserved. So the conservation of mass throughout the system must be satisfied, and this is done by requiring the total flow into a junction to be equal to the total flow out of the junction for all junctions in the system. Okay, so we have to see that equation for the mass balance should be satisfied. The second one, which is about the pressure drop and the head loss between two junctions, must be the same for all the paths between two junctions. So here we are talking about this kind of situation. So the head loss or the pressure drop between the two junctions, it should be the same. This is because the pressure is a point function and it cannot have two values at a specified point. In practice, this rule is used by requiring that the algebraic sum of the head losses in the loop to be equal to 0. Okay, so what we can see from here, that the head loss that is at this point, it should be the same head loss that is at this point. So because this head loss or the pressure drop is a point function, so it cannot have two values for the at 2 points of the piping systems. Okay, for this one, if we have the same head loss here, we can have the same value for the head loss at this point. Now let us see the pumping systems with pumps and the turbines. Now in the pumps, you can see that, for example, this one is a tank 1 and this is the tank 2, and the fluid or the water is being pumped from the lower tank to the higher tank with the help of some pump. Okay, so here we have the journal energy equation in the form of head. So we apply this equation and we apply this equation, and we will see the assumptions on this figure. So we will apply the assumptions here, and what we can see that at point 1 and 2, P1 and P2, it is an atmospheric pressure. The velocity, it can be taken as 0 due to the large area, and then we can rearrange there is no turbine in the system, and there is yeah, so we can simplify the equation in this form. The useful head of the pump will be equal to Z2 minus Z1 plus HL. So we can simplify this equation, that we can also see here after simplification of the journal energy equation. And from chapter number 5, we have seen that the pumping power requirement, which is the useful pumping power, it will be equal to the mass flow rate multiplied by gravitational force and the useful pumping head. So we can have this equation from the chapter number 5. We have seen this one. If we are dealing with a pump and the motor system, we have to multiply the efficiency of the pump with the motor, so we can get the overall efficiency. And we can also see these equations in chapter number 5, in which we can calculate the shaft power of the pump in terms of power, having the units for the watt, and then we can write this equation in the form of mass flow rate, gravitational force, head for the pump divided by efficiency of the pump. And if we are dealing with the electricity generation in terms of power, then we have to take the efficiency of the pump and the motor system as a whole. Okay, so we have seen this equation in chapter number 5 that we can also use in this chapter to calculate the value for the shaft power and for the electrical energy requirements. Okay, so why we are using these equations here, because there is a factor here, H pump useful, which is the useful pumping head in this equation and also in this equation. So somehow in some of the numericals you will see that we need to calculate this useful pumping power using these two equations that we can finally use in this equation to get the value for the head loss or to get the value for the delta C. So now let us discuss about the characteristic pump curves for centrifugal. Now let us talk about the characteristic pump curves for centrifugal pumps, the system curves for the piping system, and the operating point. Now this line, basically this kind of graph you can get with any of the pump that you buy from some industrial pumping manufacturing unit. So what information we can get from this kind of chart? So this green line, it represents you the head for the pump, which is the useful pumping head. This dotted red line represents the efficiency of the pump. So what is an efficiency of the pump? That at a maximum head, what should be the value for the volumetric flow rate? And this green dotted line represents the system curve. So we will see that each of these curves one by one. So what is this head for the pump? It tells you the relationship between the head of the pump and the volumetric flow rate. Okay, so as the head of the pump is decreasing, what we see that there is an increase in the volumetric flow rate. Okay, so what we see here, at zero volumetric flow rate we can have the maximum head of the pump, which is called as shut-off head, in which we do not get any kind of volumetric flow rate, but the head that we can get from the pump, it could be maximum. Now the alternate, what could be the thing? If we get the maximum value for the volumetric flow rate, we can have the zero value for the head. So there is a trade-off between the head and the volumetric flow rate, and you can see this one from this green line. The second line here, which is about the efficiency of the curve, as I told you earlier, we need to select a pump that can utilize the minimum energy and it can give you the maximum head and the maximum volumetric flow rate. But we can have this kind of curve for the efficiency. So there will be maximum efficiency of the pump when the volumetric flow rate, it could be 2.5 meter cube per second, and the height or the head that you can get, it is maximum 40. If you shift right or left hand side of this curve, you will be having less efficiency of the pump. What does it mean? That you are supplying more energy in the form of electrical energy, but you are not getting the useful work out of the pump. Okay, so it depends on the requirement that where you want to install the pump, and that requirement, it can be provided by a system curve. So system curve, it represents you the line in which it represents you the line for the requirement of the pump. Okay, for example, in industry you are supposed to get a value for the head to be 20 meter and the volumetric flow rate, it should be 4.2 meter cube per second. Then you have to operate the pump at this point, which represents the operating point. So although at this point you will be having less value for the efficiency, maybe 50%, but this is the requirement. So the requirement of the pump, it represents you the point in the industry where you want to install the pump. Okay, so sometimes we need to see this operating point, and then we have to reselect the pump that at this point you will be having the maximum value for the efficiency. Okay, so we can change and select the pump based on this operating point. Okay, so this is just for the information. Maybe you can go through your books and you can see the different types of pumps. These pumps are only for the centrifugal pumps. Okay, so in industries you can have like many types of pumps: centrifugal, reciprocatory pumps, and the piston pumps. So there are like 20 different maybe forms of the pumps. Okay, so it depends on the requirement on the industry, and depends on the volumetric flow rate requirement, the head requirement, the type of fluid you are dealing with. So there are many factors. Okay, so you can go through the section for the pumps by yourself and see what are the different pumps that we can use in the industry. Now let us solve this example, which is example 8-8, gravity driven water flow in the pipe. So what we have here, water at 10 degrees C flows from a large reservoir to a smaller one through a 5 centimeter diameter cast iron piping system as shown in the figure. Determine the elevation Z1 for the flow rate of 6 liter per second. So we are provided with the flow rate in these piping systems, and the temperature is given. The diameter for this pipeline, it is 5 centimeter, right? Now in this kind of situation, what we can see here, when the fluid, it is entering from the bigger reservoir into the smaller pipeline. So this one is a pipe inlet system, right? So the water is entering from reservoir to the pipe. So there is some head loss here and the loss coefficient here. The value for that loss coefficient KL is 0.5. Then this is the pipeline which can cause the major head loss due to the friction in the pipeline. So so you have to see that what should be the value for the friction factor. Now there is a bend in this pipeline. So regarding this bend here, the value for the KL, it is 0.3. Then again there is a pipe here, and you have to see that what is the major head loss due to this pipeline. Then again there is a bend. You have to see what is the value for the KL for this kind of bend. Then again you have to deal with the pipeline. Then there is a valve here having some value for the KL, and then this is a system for the pipe exit into the reservoir. So the value for the KL is 1.06. So you have to incorporate the major losses in the piping system and also the minor losses in the piping system to calculate the total value for the head loss. So what we can do here, first of all, we are dealing here with the cast iron piping systems. Okay, so the cast iron piping system, we have to first see what is the roughness of the cast iron pipe. So you can go back to this table where we have the chart for the different pipeline. Okay, so for this cast iron pipeline, the roughness is 0.0085 feet, and in terms of millimeter, 0.26. And then you have to divide this roughness with the diameter of the pipeline. So when you divide this one with the diameter of the pipeline, you will be getting the value for the relative roughness. Okay, so the roughness of the cast iron, it can be 0.0026 in terms of meter, and then we need to calculate the value for the relative roughness value, right? So what we can do at the end, we have to use this journal energy equation, and we have to apply the assumptions on this equation. So P1 and P2, we can have the atmospheric pressure. We can remove, similar is the case with the V1 and the V2. So we can remove that one. There is no pump in the system, no turbine in the system, so we can remove those parts. Okay, so the equation that we get here after simplification, that is Z1 will be equal to Z2 plus HL. Now HL, you have to consider the major and the minor head losses, HL major and HL minor, and this is the complete equation for the major and the minor head losses. Now the value for the friction, how you can calculate the value? You need to have the value for the Reynolds number, so you can calculate the value rho ud divided by mu. So velocity, it can be calculated here, volumetric flow rate divided by cross sectional area. You will be getting the average velocity. Now in this equation, you will put the value for the density, velocity, diameter, viscosity, and the value that you get here, it is 117,000, which lies in the range for the turbulent flow. Okay, so because this one is a turbulent flow, we need to calculate the value for the relative roughness. And so we have to divide the roughness of the cast iron pipe with the diameter of the pipeline to get the value for relative roughness, and then we can use the Cool-Brooks equation or the Moody chart or the Holland equation to get the value for the friction factor, this value friction factor. So here we have used the Cool-Brooks equation to get the value for the friction factor, that comes out to be 0.0315. And then for the minor head losses, we have to see what are the total minor head losses in the system. There is one entrance here. Okay, so head loss that is caused here. Then we have two elbows here, so we can multiply 2 with the elbow, loss coefficient of the elbow. Then there is one valve in the system, the loss coefficient of that valve, and the pipe exit KL value. So you will be getting the total value for the KL, and then in the total head loss equation, you will plug the value for the friction factor, length. Now the length here, you have to put the total length of the pipelines. Okay, what is the total length? This is what is the length here. This one is 80, right? So this one is total 80 plus this one, that is 89, sorry. Okay, so here you have to put the value for the complete pipeline, that is 89. Diameter is given, the total KL value is given, the velocity you have calculated, the G is given. So you will put the values and simplify the equation. It will give you 27.9 meter, that is the head loss. And then you can use this equation again, Z1, which you need to calculate, that is equal to Z2 plus HL. So you will put the values here, and the value for the Z1 comes out to be 31.9. So this is a very good example in which we have dealt with both the major head losses and the minor head losses. and this is all we were studying in this chapter until now. Okay, so you can go through this example and let me know if you feel any difficulty.